Good morning, everyone. Myself Preeti Jalinder Datir, and my topic is the impact of draft tube variations on a Francis turbine's hydraulic performance. So, in this, it contains problem statement, design and performance parameters, analytical solutions with graph analysis, 3D model, and model on Francis turbine, conclusion and references. So the problem statement is that we have to study the impact of draft variations on Francis turbine's hydraulic performance. This study explores the interplay between design parameters and efficiency, power generation and flow rates. So we are working on this problem statement. In this we are going to have different variations on Francis turbine's hydraulic performance. Design and performance parameters. So the draft tube is a crucial component in the hydraulic performance of a Francis turbine. We all know this, and it plays a significant role in improving the overall efficiency and performance of a turbine. The primary function of the draft tube is to recover the kinetic energy from the water leaving the turbine and convert it into the useful pressure energy. We all are aware of the primary function of the draft tube, and in all of this, if the crucial component isn't playing its part, then the performance of the hydraulic performance of Francis turbine will be depleted. So in order to improve the overall efficiency and performance of turbine, the draft tube is very crucial. Design parameters we are going to consider are guide vane thickness, blade velocity, inlet velocity angle and outlet velocity angle. And performance parameters we are going to consider are continuity and momentum. Design steps and formulae. Guide vane, in this we are going to see the guide vane thickness. To determine the flow rate and head, we have to start by determining the operating conditions of the turbine, including the flow rate and head. The height difference between the water source and the turbine inlet. These parameters will significantly influence the design. To evaluate guide vane profiles, we have to select the type of guide vane profiles that are suitable for our specific operating conditions. This may involve evaluating various vane profiles to find the one that provides optimal hydraulic efficiency. So the main thing is, this may involve evaluating various vane profiles to find the one that provides optimal hydraulic efficiency. We have to calculate blade thickness as well. To calculate the appropriate guide vane thickness based on the selected vane profile and design parameters, we have to choose the thickness that will be designed to withstand the hydraulic forces and stresses generated during this operation, because the hydraulic forces and stresses are going to be generated in this. Next is the blade velocity. To determine a design speed, we have to define the desired design speed for the Francis turbine, because the blade velocity is related to the rotational speed of the runner and the runner's diameter. It should be chosen to maximize turbine efficiency. We have to select the runner blade profiles. For that, we have to choose the runner blade profiles based on the design speed and specific operating conditions. That will contain the blade profiles should be selected to ensure that The flow is controlled efficiently while minimizing hydraulic losses. In this, blade velocity and draft tube efficiency are gonna be taken into the consideration. These are the calculations we have done in this. So we got the guide blade angle from inlet velocity triangle, and second one we got a diameter of the runner at inlet and outlet, and width of the wheel at inlet. Second calculations, this is the discharge versus efficiency graph. This is the 3D model on draft tube. So we all know that the Francis turbine contains runner blade, draft tubes, spiral casing, guide vanes. So we are gonna take some cases, case A, case B and case C. We have done the calculations, we have done the 3D model of this, and now the conclusions are like the hydraulic efficiency and head of the model Francis turbine with different values of the guide vane thickness. From the viewpoint of guide vane, it is noted that the efficiency and mass flow are increased as the guide vane thickness decreases due to its least drag force. So here it is noted that efficiency and mass flow are increased. Efficiency and mass flow are increased as the guide vane thickness decreases, and guide vane thickness decreases due to its least drag force. And these are the results shown in the right corner, case A, case B and case C. We can see the difference clearly. In order to confirm the vortex roof characteristic and hydraulic performance of Francis turbine, the effects of various parameters like the draft tube and 4 different values of thickness of guide vanes were investigated. So we have come to the conclusion that the efficiency and mass flow rate are increased as the guide vane thickness decrease due to the least drag force. So here the drag force is also making a huge impact and is playing a crucial role in this. So the conclusion is like this. In the study, the flow characteristics of a Francis turbine were simulated with 3 different guide vanes, which are the flow characteristics, its continuity and momentum we have taken into the consideration for different guide vanes and draft tube profiles. In particular, the vortex core and pressure distribution in the considered hydraulic turbine were investigated, and based on that data from the CFD model, the following conclusions are obtained. The guide vane of type D showed the highest efficiency value among the others, although this model improves the efficiency 1.3% more than the worst model. For better understanding of this fascinating flow problem, however, it may be necessary to perform the experimental work. In the near future, we would be glad to compare these numerical results with those obtained by anyone in the same field. As CFD plays the huge role in predicting or in defining, or it helps in the designing different things, and it is necessary to perform the experimental work as well. So we are on the conclusion that the highest efficiency among the others is shown because this model improves the efficiency up to 1.3% more than the worst model. The references we have taken from Kiran Patel, Jamin Desai, Vishal Chauhan, and Shahil Charnia's development of Francis turbine using computational fluid dynamics paper, which was the 11th Asian International Conference on Fluid Machinery and the 3rd Fluid Power Technology Exhibition. And second reference is from the Manoj Kumar Shukla, Rajiv Jain, and Professor Vishnu Prasad and S.N. Shukla's CFD analysis of 3D flow for Francis turbine by MIT International Journal of Mechanical Engineering. And the third reference is from Ruchi Khare, Dr. Vishnu Prasad, and Dr. Sushil Kumar, CFD approach for flow characteristics of hydraulic Francis turbine. In this PowerPoint presentation, I have not added the literature review, but the references are enough for this. And so, thank you.